Okay, today we're looking at Taylor's theorem and the Lagrange form of the remainder. So we've already looked at approximating functions. And so say we want to make sure that we want to see how accurate it is, basically. So for example, if we have f of x equals cos x and we want to use polynomial function to determine the value of cos of pi within a certain level of accuracy, then in this case, what if we want it to be within 0.0001 accuracy? If we have decimals, we can take a look at the graphs and check that out. And so that's what I will do right now, although I am at home and looking at this, it doesn't look quite like quite as accurate as I've done before. In any case, I've graphed the polynomial function from n equals 0 to a. Right now it's at a equals 4. And then I've graphed y equals cos of x. So if you look over here at pi, you can see that there's a gap there. So the red graph, which is the polynomial approximation, is accurate. Certainly remember it is accurate around x equals 0, because that's the polynomial function we are using to approximate this. It's a little bit off for x equals pi, with only using these 4 terms. So then if 5 terms that would be when n equals 4. A equals 5, it gets closer, right? And you can see there closer and closer as you increase the number of terms, okay? Just can't get, unfortunately, I haven't got the settings correct to get the values to 4 decimal places for each point on decimals. So in any case, let's go back to our notes here, and we're just going to fill this in because I have done it more accurately. And so basically, we would need 8 terms, okay, in order to approximate this to that degree of accuracy. And so that ends up being the 14th degree. Okay, so basically this part here is accurate within that value, and this would be considered sort of your remainder. Okay. So if you look down on your sheet here, we've split it up now. Okay, so in the 2 parts here, so now this goes to infinity from n equals 8. This goes up to n equals 7, and then that's n equals 8. So really the difference in the value of cos pi and the polynomial function where n is 7 goes from 0 to 7 is going to be equal to that remainder, that extra part here. So that's from 8 to infinity, and that is less than 0.0001. So we call this the truncation error, because really you've truncated it with a certain polynomial, in this case degree 14, so you've cut it off. So you've truncated the series, and we only use the minimum number of terms required to satisfy, in this case, the requirements of that error. The terms that are left out form the remainder or leftover part of the series. Oops, sorry about that. So let's just go here slowly. Okay, slowly is the key. Just a sec. It's easier to figure out the number of terms required when you do have good technology with good accuracy. But if you don't, then what do? Now remember, cos of pi, we really wouldn't do this. We have a calculator that can give us many decimal places, but this is for other values. And certainly when you get into computer programming and you want to make sure if you're approximating cos of pi or cos of x with a Taylor polynomial, you want to get it within a certain accuracy if you're using it in a computer program. So Taylor's theorem, there's basically the formula that we've used. This goes up to n, and remember, then we've got our remainder. Basically, that's our summation part. That now we're basically saying that that remainder is equal to the next term. We're assuming that, well, these are going to converge, right? So the rest of those terms are getting smaller and smaller and smaller. So this is really the biggest value of all of the rest of the terms, right? The next term after the nth, okay? And so the difference there, really, oftentimes we take the absolute value. So here, the absolute value of r, you can put these in here, is the absolute value of all of that. For some c between a and x, okay? Let's see. And so on Schoology, there is a document. I think I've scheduled it for you to read tomorrow, but it is on Rolle's theorem, so you can take a look at that and read through that for some extra information. We go to the next page. So basically, the Lagrange form of the remainder, that's what we've just gone through, and it's basically saying, so in here, this difference, say if I called this value c, so that difference in there between the actual function, so this is your y equals cos of x, and this is your approximation. Okay. So using Taylor's theorem and the Lagrange form of the remainder, we can determine the maximum error. So this is where math, sometimes we think it's always an exact certain value. This is where we're going to find an m value, basically a nice value. Like sometimes it might be e, sometimes it'll be just a natural number that's closest to approximate the next derivative. Okay, so m is greater than or equal to f of n plus 1 at that c value. Okay, so notice here, actually, yeah, notice here I did put a positive integer, so a natural number. So likelihood is that maybe it won't be e. Just trying to think, but none of these ones that we are doing. But that doesn't mean you can't use that. It's just for this form, we're going to use for our work in this course, a natural number. So you'll notice there's a blank here. That's because when I made it up, I wasn't sure what degree I wanted you to do it to. So it says find the maximum error, and we want to do this for an 8th degree Maclaurin polynomial to approximate cos of 4 pi over 5. So 8th degree for this is when n equals 4. So remember, if you take a look back at the formula, you will have, okay, so back to, sorry, I took a little break there. Cos, remember, is approximated by a series with x to the 2n. So when we're talking about an 8th degree, that's when n is 4. So we're going to find our remainder here. So we call it R4. That's the remainder for when n equals 4. So it's really for the next term. 4 pi over 5, that's our x value. That's going to be less than or equal to m over, and then n, oops, not n, we want to put the value of n in there. So that's going to be 4 plus 1 factorial, absolute value of 4 pi over 5 minus 0, okay, to the 4 plus 1. So now here's the question, what's m? So let's think about the next derivative. So if we're taking, remember, the derivative of cos, so the derivative of cos of x is negative sine of x. Derivative of sine of x is cos of x. So think of the values that you get. No matter what x it is, the maximum value of negative sine of x and cos of x is going to be 1. So all of these have values. Oops, sorry. Between, so values between 1 and negative 1. Okay, so that means our maximum value that we would ever get, no matter what degree it would be less than 1. So that's what we're going to use for our m value. So over here, 1 over 4 plus 1 is 5 factorial, so that's 120. And then you can convert to decimal form. Remember, you're allowed your calculator, so I'm just going to show a bunch of decimal places here. I evaluated that. And then evaluating that, again, you can pause this while you enter in your calculator if you need to. And to 4 decimal places, 8356. Okay, so that's the maximum error is 0.8356. Okay. Next one, maximum error when we're using a 4th degree Lagrange polynomial to approximate e equals 0.2. So remember e to the x, we've approximated that. It's approximated with n equals 0 to infinity of x to the n over n factorial. It's much easier than cos of x. And so if we're looking for 4th degree in this as well, then that means we're looking for when n equals 4. Okay, so that means n equals 4. So same R4, but now it's our value is 0.2. So 0.2 less than or equal to m over 4 plus 1 factorial. Okay, so this is always the same. It doesn't go back to this form. We're going to look at that formula for the remainder. So this is approximating it. So then this is 1/5 minus 0 to the 4 plus 1. Okay, so then that's going to be less than or equal to. Now we have to figure out what m is going to be. So we want to look at the 5th derivative of, so the 5th derivative, well, derivative of e to the x is e to the x. So the 5th derivative is going to be e to the x. It doesn't really matter what degree we're going to do. It's always going to be that. So that means if we put in to that derivative 0.2, that if you use your calculator is 1.2214. So again, we're going to go to the maximum value that's closest to that. It's in a natural number, so we're going to let m equal 2. Not 1, it rounds to 1. We've got to go up from there. Maximum. This has to be less than it. So that's going to be 2 over 120. And then the decimal form, again, use your calculator. And then your value is very accurate in this case. It's actually a repeating decimal. I'm going to leave it like that.